This is going to be kind of a lighthearted and hopefully fun session because from next week I'm going to start complexity theory. So I'm just going to compensate for it by letting you play games today. So we're going to talk about what we call combinatorial games. And these are games that have these properties. So first of all, these are two-player games. So we always have two players. And I will ask for some audience participation today. I will ask you to come here and actually play some of these games. And the games are turn-based, which means that, well, you take turns moving. So player one moves first, and then after the first move, player two moves, and so on. They're impartial in the sense that the moves that you have does not really depend on which player you are. So from a particular state of the game, if player one can make some move, player two can make the same move as well, and vice versa. Okay, so for example, chess is not an impartial game because if you're playing chess, you can only move your own pieces. So at every state of the game, the different players have actually different moves that they can make. So we wouldn't consider games like chess. Our games are impartial. And our games are also terminating, meaning that they will terminate. They cannot just run forever. Okay, so every play of the game will eventually terminate. And we always have one rule, and the rule is that you win if your opponent cannot move. Okay, so the person who makes the very last move in the game is the winner. These are our rules. So I need 2 volunteers for game number 1. So our first game is actually very simple. I'm going to have a token. And let's say that this token is placed here in this graph. And whenever it's your turn, you can move the token by moving it through one of the edges. So you can take one of the outgoing edges and move the token there. Okay. Now, does this game satisfy the requirements that we wrote here? Well, it's a 2-player and turn-based game. That's by definition. Is it impartial? Yes, because I'm not saying that some vertices belong to player 1 and some vertices belong to player 2. I'm just saying you get to move whenever it's your turn. And you have the same moves no matter if you're player 1 or player 2. Okay? And is it terminating? Well, in order to say that this game is terminating, I have to somehow show that it's impossible for the players to play this game forever. Right? In this case, my graph is a DAG, hopefully. And because it doesn't have a cycle, you cannot play forever. So this game is going to terminate. Does it have a cycle?
Yes. Yes.
Where's the cycle? Oh, this one? Ah, okay. This wasn't supposed to happen. Let me change the direction to this. Now it doesn't have a cycle, right? Hopefully. Okay, I need 2 volunteers. Okay, who wants to play first? So now you get to make the next move from here. Oh no, that one is not connected. Oh. Okay. Yeah, that was a bad move.
Yeah.
Yeah.
Wait.
Yeah, change the color to blue. Yeah, it's not easy teaching you these things, right?
It's quite hard to control.
Yeah. Okay. So you lost, you won. Great job.
Make a blunder.
Okay. But we're going to have another assumption in our games. And the assumption is that the 2 players are infinitely smart and they're never going to make any wrong decisions. So you're always going to make the best possible decision. Did this really happen here? Not really, unfortunately. There was a mistake at some point. So here's the thing. At this point, when the blue player was here, the red player went here, which would make him lose the game. But if the red player had gone here, then maybe he could have won, but not really. We will see soon. So let's say that I want to solve this algorithmically. I've given you the graph. I'm asking you if both parties are infinitely smart and they never make any mistakes, who's going to win? Okay. So here's what I can do. I can label the vertices of my game, which are basically the states of my game, as either winning or losing. So I say a state is a winning state if when we start the game at that state, the player who has the turn has a strategy to win. And I say it's a losing state if when we start at that state, no matter what this player does, the opponent has a way of winning. So let's just label our states with W or L to see what's a winning state and what's a losing state. So if I look at the very last state here, this is a losing state because this is by definition. If I find myself here and it's my turn, I cannot make a move. And the definition of winning is that you win if your opponent cannot move. So if you cannot move, your opponent is winning. So this is a losing state. Okay. Now, as soon as I have a losing state, any state that has an edge to the losing state is going to be a winning state, right? So if I'm here or here, I can always go to the losing state with one transition, and then my opponent is the one who's forced to lose, right? So this would be a winning state, and this would also be a winning state. Now, if I have a state that has edges going only to winning states, what does that mean? It means that it's my turn to move, and no matter how I move from the next state, my opponent is going to win. So I'm going to lose, right? So this is a losing state. Oh, well, not so sure yet because I haven't found this one. So this is a losing state because it only has edges to winning states. But what can I say about this state? Is this a winning state or a losing state? Yes, it's a winning state because as long as you have even one edge going to a losing state, you can play optimally. This is the definition of not making any mistakes. And then your opponent will be in a losing state. Your opponent will lose, you will win. So this one is actually a losing state. So actually, you played optimally. Sorry. Yeah. You guys were good. Okay. So this is a losing state. Is it? Oh, no. Okay. I have to first find this one. So this is a winning state because it goes here. So yes, this is a losing state because it only has edges to winning states. Oh, this one, what am I doing? I have to do this in topological order and somehow I cannot find the topological order here. Okay, so we found these things. I need to find this one. So this one has only an edge to a winning state. So this is a losing state, which means that this one is actually a winning state. Oh, so you didn't play optimally. So when the game was here, you had to go to this losing state to make your opponent lose, but you went to a winning state and you let your opponent win. Okay, so this is a losing state, which means that this one is a winning state because it has an edge to a losing state. And finally, the very first state, this is also a winning state because it has an edge to a losing state, which means that the very first move we saw here was also not optimal. You should have gone to this losing state to make your opponent lose. But you went to the winning state, let him win. He didn't take the win. He went to another winning state. And then you, okay. So this is how we can find the winning and losing states in a game. This is basically just doing topological sort and then doing dynamic programming on the DAG, right? But it's not always that my game states are exactly vertices of a DAG, right? So maybe I have some other kind of game structure. I can always create a DAG. I can create one vertex for every possible state of my game. And then, of course, if that doesn't lead to a DAG, that means that my game has a cycle and then it doesn't always terminate. So we don't consider those games. But if it's a DAG, I can always just find the winning and losing positions. And of course, my runtime is basically O of the size of this DAG, right? But the problem is that this DAG can actually be pretty big. So let's do another game. This is game 2. I realized that I had a cycle, so I'm gonna do this. So this is basically 2 copies of our game 1. Okay. And initially, we have two tokens, one here and one here. Now the two players start playing, and in their turn, they can choose one of the two tokens and move it. But they cannot move both tokens at the same time. They cannot also choose that I don't want to make any moves. They have to make a move. They have to choose one of the tokens and move it through one of the edges. And again, just as before, the player who cannot make a move loses. Two more players. Okay, maybe just write one or two. So write one here, and then you write two so that we know who made each. Okay. 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 Did you go? Did you? Ah, okay. You can bet now.
Yeah. Oh, fine.
You don't really have a choice.
Yeah.
No, okay, we understand what's happening. You went to the last vertex. Okay, nice. Great. They didn't really play the strategy I was thinking they would play. So I need someone to come play against me now. Go first.
How do I write on this thing?
So this thing is mapped to the screen.
Ah,
When you get the pen close, you can see the cursor on where you are, and then you can write.
okay.
Okay, I'm player 2, so let's see what I'm doing. Yes, I hope that's caught in the recording. That's exactly what I'm doing here. No, you cannot go there.
Can? Okay, you go there.
Yeah, it's the token is here, so you can only move it.
Ah,
You have to respect the direction of the edges.
okay.
Okay. You can move in the second one if you want to.
Oh, I can move your tokens too.
Yeah, you can move any of the two tokens that you.
Ah. Okay, can I move yours then? Ah.
Thanks. You didn't really have a chance here.
Yeah.
Okay, so I guess you figured out what the strategy is here. I'm just copying what he's doing because I have two copies of the same game. So if player 2 just copies the play of player 1, because I can always do the copying, I will never run out of moves. And because the game terminates, it's player 1 who will run out of moves. Right? But of course, instead of being smart about this and trying to find a particular strategy, I could just apply the algorithm from the previous game, right? It's just that now I have to think of a much bigger graph because every state is not just one vertex, it's two vertices. So every state of my game is a pair that tells me which vertex of the first graph I'm in and which vertex of the second graph. And then I will create this product graph, and then I can compute winning and losing on that product graph, right? But the problem is that the runtime of that would be terrible. So I really prefer not to do this kind of dynamic programming here. I prefer to just find the solution on my own. Okay. Game 3. It's just 3 copies of the same thing. And again, I didn't want to have a cycle, so this is in this direction. I have to fix this one too. And let me fix this one too. Your chance to take a revenge.
You go.
Who wants to go first?
Wants to go first.
Okay, I can go.
Okay, just write 1 or 2 so that we know who made it. More interesting than football.
Where's the point out here?
So we have only one person left here.
Yeah. So now you're basically playing the same game
Yeah.
that you played last time. So can you win it now?
I remember that.
Wait, can I cheat? I want to look at the win. I think this is unwinnable, if I remember correctly.
Yeah, you don't have any choice. You have to
Yeah,
just
you
make
have
that
only
one.
one
You have only one possible. You have only one possible to.
Yeah, this is unwinnable.
Yeah, only one there.
Yeah. And then I lose.
Yes, nice. Okay, this was the revenge. Okay, great. So you saw that this idea of copying didn't work really well here. Because basically when you're doing the copying, you're canceling out 2 of these copies with each other, right? So it's as if these 2 didn't exist. But of course, when player 1 loses in the 2 copies, cannot make any moves in these 2 copies, he will make the first move in the 3rd copy. But in the first game, we saw that the person who makes the first move has a strategy to win. So you shouldn't actually have copied him here. Okay, nice. So again, if I want to solve a game like this, I can consider all the possible states. So I can say I have 3 graphs here. Let's say this is G1, this is G2, and this is G3. And basically my entire game graph is going to be G1 times G2 times G3. Okay, what do I mean? I mean that let's say the vertices here are V1 and the edges are E1. Here I have V2 and E2. I mean, of course, all of them are the same in this case, but they don't have to be the same. I can have different graphs. And G3 is V3 and E3. So what is the state of my game overall? It's basically the state of 3 tokens. Where are my 3 tokens? So I can define a game G. And here, let's say my vertex set is V and edge set is E. And V is basically going to be V1 times V2 times V3. Right? So every vertex of my game, every state of my game is just going to tell me where I am in G1, where I am in G2, and where I am in G3. So that's just the location of the three vertices. So let's say I'm at V1, V2, V3. This would be the state of my game. Now, from this state, where can I go? I said that we can move in one of the three graphs, right? So from here, I can either go to V1 prime, V2, V3, where there should be an edge from V1 to V1 prime in the first game. So V1, V1 prime should be in E1. Or I can make the move on the second component. So I can go from V1, V2, V3 to some other vertex, but I will keep V1 the same. I will change V2, and I will keep V3 the same. And again, here I need that V2, V2 prime is in E2. Or I can do the third component, right? So this is taking a long time to write. So V1, V2, V3 prime. And here I need that V3, V3 prime are in E3. So these are actually the definitions of all the edges that I have in my overall graph. So these are the edges that I have in. Now, of course, I can consider this whole big graph, and then I can compute the winning states and losing states in this big graph. And according to that, I can also find the best strategy, and I can find out who wins. Okay, so our best strategies are always the same. It's just that if you're in a winning vertex, go to a losing vertex. If you're in a losing vertex, it doesn't matter what you do. Like, no matter what you do, you will lose. Okay. We have another game. So let's say we have two non-negative integers, x and y. So I have written two integers here, 12 and 15. Now, at every step, you can do one of three operations. You can reduce x, or you can reduce y. You have to reduce them by some positive integer amount, and the result should also be a non-negative integer. So don't try to get real numbers or anything here, okay? So you can either reduce x or reduce y, or you can reduce both of them, but you have to reduce both of them by the same amount, okay? And of course, the rule is just as before. Whoever cannot move loses. Okay, two players. You can either reduce one of the two numbers or both of them. Just write in the next line. Okay. Hey, interesting move, making the two numbers equal, 12, 12.
Oh, no.
No, you've already moved.
Okay.
You cannot take You can win in one step. Hey, 9, 12. He gave you a chance.
Okay.
Don't make it 9, 9, please.
Okay, I know.
It's 11. Hey, this is the end of the game. Thanks. Okay. Great. Well, of course, the reason some people were laughing was as soon as you have 12, 12, you can just directly go to 0, 0 and win the game, right? So if the two numbers are equal, it's a winning position because you can just turn it to 0, 0 and win. If the two numbers are not equal, what can you do? So let's say I start with 12 and 15 and I want to play optimally. Okay, the two numbers are not equal. What happens if I turn one of the numbers to 1? If I turn one of the numbers to 1, then there is only one move possible on that number, right? So then what does the other opponent do? My opponent would just turn the other number to 1, right? So this is actually a very bad strategy. If you want to lose, you can turn one of the numbers to 1. Or if you want to lose, you can make the two numbers equal, right? But how can I find a winning strategy? Now, here's the thing. You can, again, create the game graph. The game graph would be huge here. It will have, like, if this number is n and this number is m, it will have O, N, M vertices. And then you can find the winning positions and the losing positions in that game graph and then play according to that. Or you can just sit down and think and try to find a particular strategy for this game. But actually what we want to do in this session is to give you a general way to find strategies for games like these. But this general way is also not going to be just create the game graph and spend a lot of time computing winning and losing positions, because that's going to take too much time algorithmically. And you can imagine that if instead of 2 numbers, I had 10 numbers, that would really blow up the graph exponentially, right? So I don't want that. One last game. This is actually the game that we're going to talk about the most. So we're going to give it a name. We call this NIM. And the idea here is that you have an array of non-negative integers. So you can have more than one number or more than 2 numbers. I have 2 instances of this game here. Each of them have 3 numbers. And in each step, the player can reduce just one of the numbers. And you have to keep it a non-negative integer. Okay, so you cannot go below 0. You cannot go irrational, whatever. And of course, the player who cannot make any moves loses. Now, the point of this session is to show you that all games are actually NIM. So all the previous games that you've seen can be converted to this game. And if you can win this game, you should be able to win all of those games, assuming that you have a winning strategy. Okay, 2 more volunteers. Okay, play the game on the left. So we have 4, 1, and 3. In every step, you can reduce one of the numbers. Okay, great. Nice. Now play the game on the right. Oh, this is a golden opportunity. Can you do something that would then let you just play copycat? If you want to play, or do you want to resign at this point?
Yes, resign.
Okay, thanks. Because it's obvious that at this point, no matter what the other player does, the current player can just play copycat, right? Because we have 4, 4. So for example, if they do 2, then this one also goes to 2. If I do 1, this one also goes to 1. And then if I do 0, then this one also goes to 0. Okay, so the player who made the numbers equal is definitely going to win. Okay, but in this case, we had only 3 numbers. What if we have actually more than 3 numbers? What if I have 10 numbers? So on. What if I have n numbers? So what is the general winning strategy in NIM? So I want to go back to this concept of winning states and losing states. So you see, the condition I have is that the final states where I cannot make any moves should definitely be losing states, right? So let's just write down these conditions. My first condition is that dead-end states are losing. So if you get stuck and you cannot move anymore, that's an F. Okay. Now, a state is a winning state if it can have one transition to at least one losing state. So this is the second one, a state that has a transition to an L state is a W state. And finally, if all of the transitions out of a particular state go to W states, then that's an L state. A state that only has transitions to W states is L. Okay, so this is our definition of what's a losing state and what's a winning state. So all I need to do is to find a condition that I can easily check for the losing states or for the winning states, and then just prove that this condition satisfies these properties. So maybe my condition is that the first number should be odd and the second number should be even. If I come up with such a condition, the way that I can prove that this actually gives me the winning states is by showing that none of the dead-end states satisfy my condition, and every state that satisfies my condition has a transition to a state that doesn't satisfy my condition, and every state that doesn't satisfy my condition has transitions only to states that do satisfy my condition. If I prove these three things, I have proven that my condition is basically the winning condition of the game. Okay, so what is the winning condition of NIM? Sometimes they also call it the winning invariant. When do you win this game? Now, this might be very surprising to you, but it has to do with the XOR of the numbers. So I just take the XOR of all the numbers, and if the XOR of all the numbers is 0, I say this is a winning state. If the XOR, if the XOR of all the numbers is 0, I say this is a losing state. And if it's non-zero, I say it's a winning state. Okay, so this is the winning strategy of NIM. At this point, it's just a claim. I have to prove it. Okay, this is my claim. Let's say that my numbers are n1, n2 to nk. I claim that if I take the XOR of all of these numbers and that XOR is 0, then it's a losing state. So I say n1 to nk is a losing state if n1 XOR with n2, so on, to nk is 0. And similarly, I say that n1 to nk is a winning state if this XOR is anything other than 0. n1 XOR n2, so on, to nk is not 0. What should I prove? Well, first of all, what is my final state, the state in which I cannot make any moves? It's when all of the numbers are 0. And when all of the numbers are 0, I'm losing. And this condition says the same thing. It says when all the numbers are 0, of course, their XOR is 0, so it's saying that it's losing. So it satisfies the first condition that I needed to satisfy here. Now, I have to prove two more things. I have to prove that every winning state has a transition to a losing state, and every losing state only has transitions to winning states. Okay. So let's look at this here. If I have a losing state, according to this claimed definition of a losing state, it means that I have a state where the XOR of all of my numbers is 0. Okay. So let's say that n1 XOR n2, so on, to nk is 0. Now, what move can I make? Whatever move I'm making, well, first of all, if this is the case where all of them are 0, I cannot make any moves, and it's, of course, a losing state. But assuming that I can make a move, what is my move? My move is to take one of these numbers, one of these ni's, and reduce it. But I don't care that I'm reducing it. The thing that I care about is that actually this XOR cannot remain 0, right? Because suppose I'm changing ni, okay? So suppose I change ni to some other number. to, let's say, n prime I. And this n prime I should, of course, be less than ni. Okay, what do I know? I know that the XOR of all the numbers was initially 0. So if I take the XOR of all the numbers except for ni, so let's say I look at n1, XOR n2, so on, XOR ni minus 1, XOR ni plus 1, all the way to my last number. What is this XOR? This XOR is exactly equal to ni, right? This is just rewriting this expression, taking ni from the left side to the right side, and I'm just using the property of XOR that anything XORed with itself is 0. Okay, but if this is the case, when I'm changing ni to ni prime, this XOR on the left is not changing, it's the same thing, but this one is changing to ni prime, so they're not going to be equal. And if they're not equal, then when I move the ni prime to the left again, the XOR of all of my numbers is not going to be 0. Okay, so all I'm saying here is that if you have a bunch of numbers whose XOR is 0, and you change one of them, the resulting XOR would no longer be 0. Okay, which is exactly what I needed, because I wanted to say that if I'm in a losing position, if I'm in a position where the XOR is 0, I cannot keep the XOR 0. No matter how I move, the XOR will become non-zero. And I'm claiming that when the XOR is non-zero, the other player actually has a winning strategy. Now I have to show the last part. I have to show that if I'm in a winning state, there is a way for me to force my opponent into a losing state. So let's say that I have a bunch of numbers and their XOR is not 0. So this is now the last thing I have to prove. Suppose that n1 XOR n2, actually, let me just write it like this. XOR of all the ni's for I from 1 to k is not 0. Okay. I'm claiming that I have a move such that I can make this XOR into 0. Why do I have such a move? Why is it always the case that I can find such a move? So you have a bunch of numbers, their XOR is not 0. You want to reduce only one of them to make the XOR 0. Let's just write these numbers in binary and let's see what happens. So let's say this is my first number. I have a bunch of things. Let's say this is my second number. And let's say this is my third number. Let me also have a fourth number. And I take the XOR of all of them. So when I'm taking the XOR, I basically have to see, do I have an even number of ones for every digit or an odd number of ones, right? So here I have 3 ones, so the XOR is 1. Here I again have 1. Here I have 3 ones, the XOR is 1. Here I have only 2 ones, the XOR is 0. Here I have 1, 1, the XOR is 1, and this is it. So this is the XOR. My XOR is not 0. So I claim that I can always find one of these numbers and reduce it such that the resulting XOR becomes 0. Okay, so here's the thing. I say that my XOR is not 0. So let's look at the largest power of 2 that actually appears in my XOR. So let's look at the leftmost digit of my XOR, the leftmost bit of my XOR, that is a 1. In this case, it would be this one, right? So I have a 1 at this position. What does that tell you? It tells you that an odd number of my numbers had a 1 at this position. I'm just going to choose one of them. In this case, I have only one choice, n3. And I'm going to say I can always change n3 so that the XOR becomes 0. Now, how can I choose n3? Well, basically, I know that everything to the left of this digit was already 0. So I'm not going to touch that. Right? Now, this digit itself was 1. So in n3, I want to turn this digit into a 0. Right? But as soon as I'm doing this, This allows me to change all of the future digits in any way that I see fit. Because I changed this 1 to a 0, so no matter what I put here, the resulting number is smaller than the original number that I had for n3. Okay, so I choose these remaining digits so that the XOR becomes 0. Okay, so this one became 0, so the XOR here is 0. Now here the XOR was already 0, so I'm not going to change this digit. Here the XOR was 1, I'm going to change this one to 0, which makes this XOR 0. Here the XOR was 1, so I'm going to change this to 0, and this is going to make it 0. And actually, let me change this a little bit. Let's say I had a 0 here and a 0 here, because I want to even show you that example. So here the XOR was 1. I had a 0 here, but I'm going to change it to a 1, so that the XOR becomes 0. Okay? And no matter how I'm doing this, my n3 is actually becoming smaller. It's true that in some places I changed the 0 to a 1, but the most important thing is that the leftmost change was from a 1 to a 0. So when I'm doing this, I'm, let's say, reducing my number n3 by some 2 to the power of I, and it doesn't matter what I do with the next powers of 2, because the sum of the next powers of 2 is less than 2 to the power of. Okay, so this simple algorithm shows that basically our claim is proven. The winning strategy in NIM is to take the XORs. If the XOR of your numbers is 0, you're losing. Do whatever you want. There's nothing you can do. If the XOR of your numbers is not 0, the optimal thing to do is to make the XOR equal to 0. And then you keep playing this. So imagine I'm the player who's always making the XOR 0. So I make the XOR 0, you make the XOR non-zero. I make it 0, you make it non-zero. And the game cannot go on forever because our games are terminating. So at some point, it's going to end. But when it ends with all the numbers being 0. So it's your turn to move when it's ending. So I will always win. Okay, that's the whole point. This is the proof that we did. Again, I'm just showing that these conditions have the same properties as the winning and losing conditions. And this proves that they are the winning and losing conditions. Okay. Great. So does anyone want to play these games again? Okay, I can also show you a technique that we used to use in high school. If your numbers are less than 1024, you can use your fingers as bits, right? And you can do bit calculations, and then you can calculate XORs using your fingers. Do 4, 1, 3. What is the XOR of 4, 1, and 3? The XOR is 6. So you want to turn the XOR into 0.
6 is 1, 1, 0.
6 is 4 plus 2.
Yeah. 1, 1, 0. So change it to 0.
Another way of looking at this, just look here, it's your point. Okay, another way of looking at this when you have 3 numbers is that you want to make one number equal to the XOR of the other ones. So here, 1 XOR 3 is 2, actually. So you wanted to turn that into a 2, right?
Great.
Okay. Yeah, okay. 2, 1, 3. So now the XOR is 0. Your move, you can use the other pen. Yeah, there's nothing you can do. Sorry.
So I just want to make the game end as quick as I can.
Okay. 2, 1, 0. Nice. Now the XOR is 3. 2 XOR 1 is 3. So you want to make it into an XOR of 0. Yeah. 1, 1, 0. And now, I mean, you have only one move really, because there are 2 moves, but they're pretty much the same. You have to turn one of the ones into a 0. So yeah, 0, 1, 0. Nice. Now start the next game. No, you play first. Okay. 0, 8, 12. You want to make the XOR 0, which, I mean, An easy way of making the XOR 0 is to make the two numbers equal if you have only two numbers. So this also gives you the optimal strategy when you're playing NIM with two numbers. The optimal strategy is to make the two numbers equal and then play copycat. Okay. Yeah, he just gave up. I mean, you can try going for like 0, 7, 8, hoping that your opponent makes a mistake.
I think he will not because he's already to same number.
Oh, let me give it a try.
The mediation.
Okay, thanks. Okay, great. So now you know how to play NIM. But you see, the really weird thing here is that if I have several copies of NIM, it's just like one copy of NIM, right? So remember the very first game that I gave you here, this was a game on a graph. And then I said, what if I have two copies of this game? So what if I have two graphs, and in every turn you can make a move in only one of the two components of the game? So in this case, the game actually changed. But if I do this with NIM, the game doesn't really change, right? So let's say I tell you that instead of just having this game on the left or this game on the right, you have both games together, but at every turn, you can just make a move in one of the two games. It's pretty much the same thing. It's just that you have 6 numbers. Now you have to look at the XOR of 6 numbers, right? So this is a very nice property of NIM, that if you play several copies of NIM side by side, it's just like playing NIM. So now I want to show you that any other game is also NIM. Okay. So let's take this game. And let's turn it into NIM. So what we're going to do here is that we're going to assign a number to each one of the vertices of this game. And the idea is that if I assign a number k, I think of this vertex as being as having the same role as the number k in my NIM game. So I want to transform this game into a NIM. And the way I'm doing that is that every vertex gets transformed to a number in NIM. And the numbers in NIM are called nimbers. Okay. Now, I have the winning and losing sets and so on. But let's say I want to translate this last vertex to a number in NIM. What number do you think I should assign to it? So this is a vertex where I couldn't do any moves anymore, right? So what is the state in the game of NIM where I cannot do any moves? It's when I have the number 0. So imagine that I'm playing NIM with just one number, okay? So instead of having like 5 different numbers or 6 different numbers as we had here, just imagine that I'm playing NIM with one number, okay? Then this would be very similar to having the NIM number 0 here, okay? Now, let's look at this vertex. This vertex has an edge that can go to another vertex that had a number of 0. So if you go back to NIM, what is a number that you can turn into 0 and only to 0 in one move? It's 1, right? So I'm going to say this one has a number of 1. And similarly, this one has a number of 1. Okay. Now, let's say that I have another vertex here. I'm just going to add another vertex that has an edge to this one and an edge to this one. Okay. So this is a vertex. Well, first of all, is it a winning or a losing vertex? It's actually a winning vertex, right? But this is a vertex that can, in one step, go to vertices with numbers of 0 and 1, right? So this is very similar to the number 2 in our game of NIM. So I'm going to assign a number of 2 to this vertex. Now, what should I assign to this vertex? This vertex has edges that go to vertices with numbers of 1, but it doesn't have an edge to a vertex with a number of 0. Or actually, sorry, maybe it does. I again forgot that this is in topological order. So let's look at this vertex. This vertex only has an edge to something with a number of 1. So what is the number that I should assign to this vertex? So in the game of NIM, I don't have any numbers that can only be converted to 1, because any number that can be converted to 1 can also be converted to 0 in one step, right? But here's the thing. Let's look at it from the point of winning or losing. This is a losing vertex, right? And the only losing number in NIM is 0. So it makes sense to assign 0 to this vertex, actually. Generally, I want to assign 0 to all of my losing vertices, because that's the only number in NIM that causes a loss. So I'm going to assign 0 to this. Okay. Another way of looking at this is that if I get to this vertex, I could only go to a vertex that was already 1, or a winning vertex. And then in the next step, my opponent could go to a vertex of 0. So no matter what I did, in 2 steps, I would be in a vertex with a number of 0. So this is pretty much the same as saying that this is also 0. Of course, like I will be losing in 2 steps instead of immediately, but I'm losing anyway. Okay, now let's look at this vertex. So this vertex has an edge to a vertex with a number of 1 and an edge to a vertex with a number of 0. So it's very similar to the number 2 in the game of NIM. So I'm going to assign a number of 2 to it. Okay. Now, let's look at this one. This one only has an edge to something with a number of 0. So it's going to have a number of 1, right? Okay. Now let's look at this one. This one only has an edge to a number of 0. So we talked about this, sorry, to a number of 1. So we talked about this. This is going to have a number of 0. Let's look at this one. It has an edge to 0. It has an edge to 1. It has an edge to 2. So this is like the number 3 in NIM. In one step, I can turn it into 0, 1, or 2. Let's look at this one. In one step, I can turn it into 0 or 1. So it's similar to the number 2 in a game of NIM. And finally, let's look at this one. In one step, I can turn it to 0, 2, or 3. So here's the part where things get interesting. I'm going to say this is similar to the number 1 in the game of NIM. Now, why is it similar to a 1 in a game of NIM? I can turn it to 2, 0, and 3, right? The important point is that in one step, I cannot turn this vertex into a vertex that has a number of 1, right? So I can turn it to 0, or I can turn it to something bigger than 1, but I cannot turn it to 1 with one step, okay? Now, if I turn it to 0, I will win the game. So that's what I would do. It would be stupid for me not to turn this into a 0, right? So even though this vertex has edges that go to places with numbers of bigger than 0, the player would never take those edges. If the player is rational and wants to win, the player will always just take this edge to 0, right? So this means that this is actually very much similar to the case where those other edges don't even exist. Because if you have some edges, but your player is never going to take them, you can just delete them from the game. Okay? Now, generally, this is what I'm going to do. I'm going to say, if I want to assign a number to some vertex V, so let's say I have this vertex V, and let's say it has edges to some other vertices. So let's call this U1, U2 to UT. Okay. The number that I'm going to assign to the vertex V is the smallest number that does not appear among the numbers of U1 to UT. So the way I write this is like this. I say max Max is the minimum excluded number. Max of the numbers number of U1, number of U2, so on to number of UT. So, of course, I can now assign the numbers using dynamic programming. I can just do a topological sort of the states of my program, and I can assign numbers. Okay. But now I want to just give you a little bit more explanation about why this makes sense. So let's say that I have a bunch of numbers here. And let's say that all the numbers from 0 to some other number. So let's say all the numbers from 0 to I minus 1 have appeared. So I have a number of 0, a number of 1, so on. And I have a number of I minus 1. Then in these successors, I might have a number that is bigger than I. So maybe I have, I don't know, I plus 10. Okay. I have a bunch of other numbers, but I don't have any number I. Okay. So I have all the numbers before I, but I don't have I itself in my successor. And I'm saying that in this case, it makes sense to just assign I to this vertex P. Now, why is that the case? Because, well, I can just do two cases, kind of. I can do the case where I is 0 and the case where I is not 0, but I can also do it without a use case. So, first of all, what can I do with the number I in nim? I can just decrease it to all the numbers that are smaller than I. And here I can do the same thing. I can go from this vertex V to vertices that corresponded to numbers smaller than I. For each one of them, I can do that. Okay. The problem is that here I can do some extra things as well. So, for example, I can turn this into a vertex with number I plus 10. I want to argue that this would not help me in the game. That I would not actually do this. Okay. Now, why is that the case? Suppose that I do this. Suppose that I go somewhere here. Now, you see, intuitively, this is because this vertex V was either a winning vertex or a losing vertex. If it was already a winning vertex, I had a winning strategy. And my winning strategy was to go to one of these places. So why lose that winning strategy and do something stupid like this? Why go somewhere else? Right? If I have a winning strategy, I'm going to win anyway. Now, otherwise, let's say that I didn't have a winning strategy. So let's say I was in a losing state. And my state is not just this vertex, because this vertex corresponds to only one component of my state. Okay? So let's say I was losing the game. So it means that if from this vertex V, I went anywhere in here, I would lose. So if I went from V to something with a number of anything between 0 and I minus 1, then my opponent had some moves that would make them win the game. But if I now go to a bigger number, the opponent has all the same moves available, right? So when I'm going from this to a bigger number, I'm actually giving my opponent more choice. If previously, let's say I went from V to a number of 1, then my opponent could only go to a number of 0, right? Now, suppose that I go to a number of 10. My opponent can still go to a number of 0. And I can generally say this for any pairs of numbers. So if I went to a number of j, my opponent could go anywhere between 0 to j minus 1. And if with that kind of strategy available to him, he could win. If I give him more strategies, if I say now you have some extra choices as well, he would just not take those choices because he's winning anyway, right? So this is the intuitive idea. Of course, I will give you a link to a formal proof of this as well. But generally, what we're going to do is that we're assigning a number to every one of the vertices of this game, or every one of the states of this game. And we use the max rule. So the number that is assigned to every state is the smallest number that does not appear in any of its successors. Okay, now, which states are winning states and which states are losing states? I can look at the numbers that I assigned, right? So 0 was the only number that would make you lose. So all the vertices that are labeled with 0 are losing vertices, and you can check it here too. And any vertex that has a non-zero label is a winning vertex. So right now it seems like I didn't really have any progress, right? So I had losing and winning, but now instead of losing and winning, I just have a bunch of numbers, and it seems like I only care about these numbers, about whether these numbers are 0 or non-zero, right? But the interesting point is what happens when I have 2 copies of the game or several copies of the game. So let's say I have this game and I take 2 copies of it. So I have this one, and then I have this one. Remember what I said about nim. If I take 2 copies of nim and I say in every turn you can move in only one of them, 2 copies of nim are just like 1 copy of nim. We just put the numbers together and take the XOR. So now if I have 2 copies of this game and I know how to map each copy of this game to nim, I know how to map the resulting game to nim, right? So if I'm starting here, if I'm starting by putting my first token here and my second token here, both of them have a number of 1. So the resulting game together will have a number of 1 XOR 1, which is 0, right? Which is actually also what we saw, because in this case, it was a losing case. The player who started would lose, right? Now imagine if I have several games, and these games can be the same or they can be different. So let me just copy my very first game, which was a little bit different. So let's say I copy this one and I add it here. So now I have the sum of 3 games. So I have 3 games, and at every step you can make a move in only one of them. I have already computed numbers for the first 2 games. Let's compute numbers for this third one. And actually, let me just remove some of the edges to make my life easier. So I don't even want that vertex. Let's say this is my third game, and I just want to compute numbers here. So the number corresponding to this one is 0. This one only has an edge to 0, so it's 1. This one is 1. This one has only an edge to 1, so it's 0. So remember, it's max. It's the minimum number that does not appear in your successors. So here 0 and 1 appear, so this is 2. Here 1 and 2 appear, but 0 itself doesn't appear, so this is 0. Oh, sorry, no. This one is 0, so 0, 1, and 2 appear, so this is 3. Here it's a dead end, so it's a 0. 0 and 3 appear, so this is a 1. Okay. So now I can also say that I can start wherever I want in these games. So let's say that I'm doing the state shown in magenta. So let's say I'm starting by putting 1 token here, putting 1 token here, and putting another token here. Now I can just take the XOR of my numbers. I can take the XOR of 1, 2, and 3, and that XOR is 0, so I know that this is a losing state. Now, what is the proof that this actually works? Well, the proof is just going to be simulating nim. Okay, so you're playing this game, but just imagine in your mind that you're actually playing nim. Right, there is kind of like a homomorphism between any game and nim now. Because here you're at a vertex that corresponds to 3. Here you're at a vertex that corresponds to 1. Here you're at a vertex that corresponds to 2. But in every step from a vertex that corresponds to some number, you can go to vertices that correspond to smaller numbers. Okay? So from here, I can go to vertices that correspond to 1 or 2 or 0. Right? And so on. Now, again, the nasty part is that you might sometimes be able to go to a vertex that corresponds to a bigger number, but then your opponent can just undo your move. What does that mean? So let's say that I start here and I'm at a vertex that has a number of 1. And let's say, oops, I broke it. I love this too much. Okay. So let's say that you start here and you're at a vertex that has a number of 1. And let's say that you can go to a vertex that has a number of 2. So it seems like it's not like the game of NIM. I could actually increase my number, whereas in NIM, I couldn't increase my number, right? But okay, I went from 1 to 2, but by definition, since this is 2, it has an edge to a vertex that has a number of 1. So my opponent can just undo my move, can take me again to a vertex with value 1. So if I ever think of doing these kinds of stupid moves that increase the number, my opponent just undoes them, takes me back to the same status as before. And if I don't do these kinds of moves, then it's exactly the game of NIM. From every state, I can only go to states that have smaller numbers. And we already know how to win in the game of NIM. It's just taking the XORs. So now if you have the combination of any number of games, you just compute numbers in each one of your components, and then you just use the XOR solution. Now, why is this faster? Because before I had to actually take the product graph of all of these components. So if each of my components had n vertices, I had to look at a graph that had n cube vertices, right? And then I had to find winning and losing in that graph. I had to do this dynamic programming based on topological sort on that graph. But now I don't have to do this. I do it in each of the components separately, but instead of just finding winning and losing, I find the numbers. And then I just use the XOR rule of NIM. And this is called the Sprague-Grundy theorem. So Sprague-Grundy says that any game is equal to a game of NIM, is equivalent to a game of NIM. And of course, any game of NIM is equivalent to a game of NIM with only one number, because you can just take the XOR of all numbers. So any game is equivalent to a game of NIM with just one number, okay? But when I say any game that satisfies these requirements that we had in our definition. So if you have a two-player turn-based impartial game that always terminates, then that game can always be turned into NIM. And given that we know the strategy for NIM, we basically know the strategies for all of these games. And if you look at the games that we played today, all of them satisfy these requirements. So this one was our most common game. This is just the combination of this game with itself. So generally, whenever you have a game like this, you can translate it to NIM. And then you can also combine any number of games like this, because combining games of NIM is just taking the XOR. So if you have a very complicated game that consists of, let's say, n different games that are two-player turn-based impartial and terminating, and then you say that every player can move in only one of the games at each turn, that's again just NIM.